In this example, we're going to look at how to calculate the area of a surface that's not confined to a plane. Specifically, we're going to look at the portion of a paraboloid described by the equation z equals 2 minus x squared minus y squared above the unit circle x squared plus y squared equals 1 in the xy plane. Let's begin by sketching this to get an idea of what the surface looks like. So we've got our x, y, z axes, and then the paraboloid opens up downwards with its vertex at z equals 2 on the z-axis. When z is equal to 0, we'll have x squared plus y squared is equal to 2, or in other words, we'll get a circle of radius square root of 2. So that's what we've got going on in the xy plane for this paraboloid. But the area that we actually want to calculate is the area above the unit circle. So here's my unit circle in the xy plane. And if I follow this up to the paraboloid, I'll get some sort of region up here. And what I'm actually interested in calculating is the area of this portion of the surface of the paraboloid. So basically, the portion of the paraboloid such that if you were shining a light from above, its shadow would give you the circle x squared plus y squared in the xy plane. We'll call this portion of the surface S, and then we'll call this region, the x squared plus y squared equals 1 unit circle in the xy plane, D. In the notes, we came up with a way of relating the area of a surface described in the form z equals f of x and y to the area of the region that sits above or below this in the xy plane. So in particular, the area of this region S, remember we use this ds to describe an infinitesimal area element for a surface that's living in 3 dimensions. This is equal to the double integral of its projection into the xy plane, this region D, of the square root of 1 plus the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared, all square rooted. And then we're just doing an integral in 2 dimensions, so this is our usual 2-dimensional area element. So for example, if we were in x and y coordinates, this would be dx dy. If we were in polar coordinates, this would be r dr d theta. Whether we should be working in Cartesian or polar coordinates is a choice we'll make in a few moments. But before that, let's first work out the partial derivatives. So we've got the partial derivative of f with respect to x, that's just minus 2x. And the partial derivative of f with respect to y is similarly just minus 2y. So plugging these into the double integral, we've got that the area is equal to the integral over the region D of square root 1 plus minus 2x squared will give me a 4x squared, plus minus 2y squared will give me a 4y squared, and then dA. So now we just have to carry out this integral in the xy plane over the region D, which is the unit circle x squared plus y squared equals 1. So how should we set up that integral? Well, notice here that we could write this 4x squared plus 4y squared as 4x squared plus y squared, which in polar coordinates would just be 4r squared. Having noticed that, and the fact that we're integrating over a circular region, suggests that we should work in polar coordinates. So let's do that. This means we'll use r dr d theta for our dA, and the region that we're going to be integrating over is all points r theta, such that r runs from 0 to 1, and theta runs from 0 to 2 pi. All right, so that integral is equal to the integral from theta equals 0 to 2 pi, r equals 0 to 1, of the square root of 1 plus 4r squared, and then r dr d theta. Notice there's no theta dependence anywhere in here. And this is because we have circular symmetry. So the integral over theta is just going to end up giving me a 2 pi. For the integral over r, I'm going to make the substitution, let u equal 1 plus 4 r squared, which gives me du is equal to 8 r dr, which is convenient because I've got this r dr here, and so I'll replace that r dr with 1/8 du. I'll change my limits of integration as well. So when r is equal to 0, this gives me u is equal to 1, and when r is equal to 1, this is going to give me u is equal to 5. So I pick up a 2 pi from the theta integral. I've got my integral now over u from 1 to 5 of the square root of u. My r dr becomes a 1/8 du, and that's it. This gives me pi over 4 when I bring out that factor of 1/8. My antiderivative is 2/3 u to the 3/2, and I'm evaluating that at 1 and 5. Factoring out that 2/3, I get pi over 6, and then plugging in my limits of integration, I get 5 to the 3/2 minus 1 to the 3/2, which is just 1. And that's my final answer. So this gives me the area of that portion of the paraboloid. And what's really cool here is that I've done this integral over this portion of a surface that lives in 3 dimensions, but I've managed to do it by relating it to an integral over a region in the 2-dimensional plane. All right, that's it for this example on surface integrals. Thanks.